This little lecture is going to talk about the normal approximation of the binomial. So if you recall, whenever we had to find binomial probabilities, we had to use a very messy formula. It was that one with the choose business, so n choose x, pi times the pi to the x, 1 minus pi to the n minus x. And we would often have to do this multiple times, so it's a whole lot of work, and we'd like to avoid that if we possibly can. And that's what the normal approximation to the binomial does for us. Another thing that this does for us is it illustrates something called the central limit theorem. And the central limit theorem will be used much more generally, so not just for binomials, when we get to the next chapter. So understanding this normal approximation of the binomial will give you a glimpse of the central limit theorem in a situation where it's a little bit easier to understand. When we get to the next chapter, it's going to get a little bit more difficult to understand it. So I've already mentioned that binomial distributions will become approximately normal provided the sample size is big enough. So I've already told you the binomial approximation part. Let's just be a little more formal with this. So if xb is a binomial distribution, or if p is the equivalent percent, then it turns out that these two statistics have approximate normal distributions as long as n times pi is bigger than 5 and n times 1 minus pi is bigger than 5. Let's take a little closer look at these formulas. So this is going to have a standard normal distribution. We take a binomial minus n pi. Now n pi is the mean. So we're taking x minus its mean, and then the square root of n pi 1 minus pi is the standard deviation. So it's like we're computing a z-statistic in the previous section. Some random variable less its mean divided by its standard deviation, and we're making that a z-statistic. Likewise, if you take p minus pi, pi is the mean of p, and then the thing that's sitting in that denominator is just the standard deviation of p. So again, it's like a normal standard deviation. Now let's go back to the problem we did earlier, which was on recall. So 60% of the people would recall seeing our ad. We called up 4 of them. You've already seen this probability histogram. And I noted at the time that it was vaguely normal, and I emphasized vaguely. But here I have a normal curve superimposed on top of it, and you can definitely see the resemblance. If we go back to the conditions, n times pi bigger than 5, well, n is only 4, so there's no way that n times pi is going to be bigger than 5. And so these conditions protect us from doing something silly like approximating this binomial with a normal. But what would happen if we turn the sample size up a little bit? So instead of just drawing, say, 4 people, what would happen if we took 40? Now notice that n times pi is bigger than 5, as is n times 1 minus pi. So the normal approximation should be reasonable. If you do this, here's the exact probability histogram, which I got from Excel using the binomdist function, and I've superimposed a normal curve on top of it, and it's a remarkably good fit. That normal curve is going right through the middle of all those bars. So I think there's something to this approximation, is my point with this graph. Now, these conditions guard against skewed distribution. So let's consider a skewed distribution and see what happens. So consider a situation where pi is now 98%, 0.98. And let's draw a sample of 100. So notice that n times 1 minus pi is only 2. That indicates that we have no business doing the normal approximation. Well, I've generated the exact binomial distribution using Excel, and it's shown in the upper left-hand corner here. I've superimposed a normal curve, and you'll see that the fit is pretty lousy. So the first thing to note is that the binomial distribution stops at 100. There's no way that you can get more than 100 yeses out of 100 tries. So the bars stop at 100, yet the normal distribution wants to keep on going. So that wreaks some havoc, kind of pushes the normal curve off, shifts it a bit, and the whole thing looks pretty bad. But if we turn n up, this normal approximation theorem says that eventually this thing should become normal. So if we turn the sample up to 400, notice that n times 1 minus pi here is going to be 8, so it's a little bit bigger than 5. The normal approximation gets a little bit better. There's almost no mass at that 400 bar, so it's not like we're going to lose much. The normal curve is going to keep going, but there's not much distribution there. And this is looking much better. If we turn it up to 1,000, it gets even better. Here's a sample of 5,000, and the two are practically indistinguishable. So even though we have a very skewed distribution, as long as your sample size is large enough, you can approximate it with the normal. Now let's actually find some probabilities. So let's take a very small problem. Let's say that we have a binomial distribution with an n of 12, and pi is exactly 0.5. So maybe we flip a coin 12 times, and this is a fair coin, so pi is 0.5. Now, suppose we wish to evaluate the chance that xb was less than 4. Well, here's an exact probability histogram. I could find that with Excel. And the normal curve is superimposed on it. N times pi is 6, n times 1 minus pi is 6. Both of those are greater than 5, so it looks like we could use the normal approximation. The other thing to note is the mean of the binomial is 6. So that's the center of this distribution. And the standard deviation is 1.73. So let's now find this probability that xb is less than or equal to 4. Now the exact probability would be given by the areas of these 5 bars. There's not much of a bar over 0, but there is just a tiny sliver there. So if we added up the areas of those 5 bars, we would have the exact probability, which binomial distribution gives us to be 0.1938 binom dist. But consider approximating this with the normal. Now, what you have to think about is that there's going to be a bar of width 1 centered at each number. Okay, so over the value 4, we have a bar of width 1. This bar starts at the value 3.5 and ends at the value 4.5. Likewise, this bar sitting at 3 begins at 2.5 and ends at 3.5. Now, if we're to find the area, and if we just started at 4, we would be cutting off half of that bar centered over 4, and that would not be a good idea. So instead what we're going to do is try to capture that entire bar. So we're going to say that the chance that we have a binomial less than or equal to 4 is going to be approximately equal to the chance that we have a normal less than or equal to 4.5. Now let's see why that works. So here is the value 4.5. That is the end of the bar that is on 4. Now if we use the normal curve and find an area under that, notice what happens. We count this little triangle up here. It's not quite a triangle since this is a curve, but it sure looks like a triangle. But we should be counting this triangle down here, but don't. All right, now what we're counting on for the normal approximation to work is that this triangle has approximately the same area as this triangle. Ditto for the bar over 3. We have those two triangles, hoping that they're about equal, over 2, over 1, and so forth. Okay, so we're going to start the bar. We're going to find the chance that z is less than 4.5. So 4.5 less its mean, divide by its standard deviation. We get minus 0.87. We can go look that up with norm dist, and we find 0.1922. So using the normal approximation, we think that the chance that we would have 4 or fewer heads would be 19.22%, whereas in fact the real number is 19.38%. That approximation is not bad. That's pretty close. Pretty close, and that's only with a sample size 12. If you turn it up some more, it will only get better. Okay, my policy on using this continuity correction is that adding the 0.5 will improve your correction, but if you don't do it on an exam, I'll still give you full credit. So if you took xb, z less than 4, minus 6 over the standard deviation. I give you full credit for using 4 rather than 4.5. You can read the rationale on this slide. Okay, I'll do some problems in subsequent videos.